In this video, we want to give an example of how the generalized implicit function theorem and the generalized implicit function rule are used. So we're going to have a system of simultaneous capital F equations. So let's suppose our first capital F function depends on y1, y2, and x, and it's equal to 3y1, y2 plus y1 squared times x minus 4. And when we set that first capital F function equal to 0, we get our first capital F equation. Our second capital F function is expressed as f2, which depends also on y1, y2, and x, and is equal to 2 y1, y2 cubed times x minus 4 y1 squared x squared plus 2. And when we set that capital F function equal to 0, we get our second capital F equation. One way of thinking about this system of simultaneous capital F equations is that y1 and y2 are the endogenous variables. So we have two equations, two endogenous variables, and x represents some exogenous variable. In terms of an economics problem, you could think of the first capital F function as a demand equation. I guess the first capital F equation as a demand equation, and the second capital F equation as a supply equation. Y1 is maybe Q, Y2 is P, and maybe X represents the exogenous variable income. So the question is, are the implicit functions or the implied functions, are the implicit functions y1 as some function of x and y2 as some function of x, are these implicit functions defined around some point? Let's say around the point y1 equal 1, y2 equal 1, and x equal 1. So to see if this is the case, to see if these implicit functions are defined, we have to go through all the conditions of the generalized implicit function theorem. So let's start with, let's call that the generalized implicit function theorem. Let's start with condition 1. At our given point, are all of the capital F equations satisfied? So we go to our first capital F equation and substitute in y1 equal 1, y2 equal 1, and x equal 1. And in this case, it makes it really simple to evaluate this, because 3 times 1 times 1 is just 3 plus, and again, remember y1 is 1 and x is 1, so this is just 1 squared times 1, which is just 1, minus 4 equals 0. Is that true? Yeah, 3 plus 1 is 4, minus 4 equals 0. So the first capital F equation is satisfied. Is the second capital F equation satisfied at the given point? Yes, again, remember, just substitute in y1, y2, and x all equal to 1. So the first term is just 2 minus, the second term is just going to be minus 4 plus 2, and is that equal to 0? Well, 2 minus 4 is minus 2 plus 2 equals 0. So that second capital F equation is also satisfied. So our first condition of the generalized implicit function theorem is satisfied. What is the second condition? All of the partials of both capital F functions have to be defined with respect to all the y's and all the x's. So in this case, we need to look at the partial of the first capital F function with respect to y1, and that's going to be term by term 3y2 plus 2y1x, and that's it. And when we evaluate this at the said point, when y1 equal 1, y2 equal 1, x equal 1, this is just 3 plus 2, which is equal to 5, and that is some defined value. What about the partial of the first Kaplan function, oops, that was y1, with respect to y2, the second y variable? What is that going to be? It's going to be 3y1, and that's it. When evaluated at our point in question where y1 is 1, this is just equal to 3. And finally, we need to look at the partial of our first Kaplan function with respect to our one exogenous variable in this case, which is just x, and that comes out to be y1 squared, which when evaluated at the said point here is just equal to 1. So again, all of those partial derivatives of our first Kaplan function are defined with respect to all the y's and our 1x value in this case. Now we have to do the same for the second Kaplan function. So we need to look at the partial of the second Kaplan function with respect to y1, and that's going to be 2y2 cubed x minus 8y1 x squared. And when we evaluate this at the said point, y1 equal 1, y2 equal 1, x equal 1, this just comes out to be 2 minus 8, or minus 6, which is a defined value. Next, we'll have to look at the partial of the second Kaplan function with respect to our next y, y2, and that comes out to be, let's see here, 6 y1 y2 squared x, and that's it, which when evaluated at our said point comes out to be 6, and that is a defined value. And finally, we need to look at the partial of our second Kaplan function with respect to x, and that comes out to be 2y1 y2 cubed minus 8y1 squared x, which when evaluated at our said point, y1 equal 1, y2 equal 1, x equal 1, just comes out to be 2 minus 8, which is minus 6, which is again also a defined value. So basically our second condition of the generalized implicit function theorem is satisfied. What's the third condition or requirement of the generalized implicit function theorem? The endogenous variable Jacobian determinant has to be non-zero. So let's see if we can form that. The endogenous variable Jacobian determinant, or the determinant of the endogenous variable Jacobian matrix, contains the following elements. What we have to do is just go back and get the first order partial derivatives of each Kaplan function with respect to the endogenous variables, the y's. So go back to our first Kaplan function and partial it in order with respect to y1 first, and then the second element in the first row will be the partial of that first Kaplan function with respect to the next endogenous variable, y2. For the second row, we do the same thing, only with respect to the second Kaplan function. So it's going to be the partial of the second Kaplan function with respect to y1, and the partial of the second Kaplan function with respect to y2. And again, we have to evaluate those partial derivatives at the said point. Well, we already have each of these partial derivatives because we've already done that work. So let's just fill in those numbers. Partial f1 partial y1 was 5. Partial f1 partial y2 was 3. Partial f2 partial y1 was minus 6. And partial f2 partial y2 was 6. So if we evaluate this second order determinant, what do we get? Well, it's the difference between the cross products. So it's equal to 5 times 6 is 30 minus a minus 18. So it's basically equal to 30 plus 18, or 58, which is not equal to 0. And therefore, condition 3 of the generalized implicit function theorem is satisfied. Oh, let me go back. This is not 58. My error here. This was 48. And still, all the conditions of the generalized implicit function theorem are satisfied. So what can we conclude? What does the generalized implicit function theorem tell us? if the three conditions are satisfied, we can conclude that the implicit functions are defined, where y1 can be expressed explicitly as a function of x, and y2, our second endogenous variable, can be expressed explicitly as a function of x as well. If you go back to our economic problem, basically we're saying the equilibrium value of Q can be expressed as a function of income, and the equilibrium price can also be expressed as a function of income. Okay, the next thing we want to do is use the generalized implicit function rule to find the derivatives of those implicit functions that are defined. We want to be able to find the derivative of y1 with respect to x and the derivative of y2 with respect to x. So how do we do that? Using the generalized implicit function rule. Well, we can go back and take the total differential of each of our capital F equations. So we're going to get partial f1 partial y1 dy1 plus partial f1 partial y2 dy2 plus the partial of f1 with respect to x dx, and set that equal to the differential of 0, which is what's on the right. The 0 is on the right side of that first cap of equation, and that the differential of 0, or the differential of a constant, is just 0. And when we do that, basically you can put those results in matrix form, as we showed in our PowerPoint slide, and basically you end up with the following result. Partial f1, partial y1, partial f1, partial y2, partial f2, partial y1, and partial f2, partial y2, times your x variable matrix, which is the derivative of y1 with respect to x and the derivative of y2 with respect to x, and those are the elements we're trying to solve for. And in our D matrix of constant terms, we have minus partial f1 partial x and minus partial f2 partial x. So again, we can kind of think of this as our A coefficient matrix, our X variable matrix, and our D matrix of constant terms. And let's just fill in those elements. This implies the following result. Well, this is just our endogenous variable Jacobian determinant, whose elements were 5, 3, minus 6, and 6. The X variable matrix, those elements that we're trying to solve for, are the derivatives of those implicit functions, dy1 dx and dy2 dx. In our D matrix of constant terms, we already solved for partial f1 partial x, which was 1, but we need the minus of that, so that first element is going to be minus 1. The partial of f2 with respect to x we already solved for, and that was minus 6, so the minus of that is a plus 6. So now all we have to do is use Cramer's rule, and we should be able to solve for these derivatives of our implicit functions. So in this case, let's see, how can we get dy1 dx? Well, we need the determinant of our A1 matrix divided by the determinant of the A matrix. How do we find that A1 matrix? We replace the first column of the A matrix with the D column vector, and then put in the remaining elements of the A matrix, all divided by the determinant of the A matrix, which is 30 plus 18, which is 48. And this comes out to be 6 minus 18 over 48. Excuse me, that's a minus 6 minus 18 over 48, which basically comes out to be what, minus 24 over 48, which is equal to minus 1/2. And finally, dy2 dx, the derivative of y2 with respect to x, is our second variable in the X variable matrix. So using Cramer's rule, it's going to be the determinant of the A2 matrix over the determinant of the A matrix. How do we get that A2 matrix? We replace the second column of the A matrix with the D column vector. So we have here 5 minus 6 minus 1 is 6 over 48, which is 30 minus 6 over 48, which is 24 over 48, which is equal to a plus 1/2.